So in general, if we have a sample space S that contains n number of subsets, we'll call this E1, E2, E3, E4, E5, E6, and so on. And I have a set A associated with S this way. The probability of A can be given by the intersection of A with all these various subsets. And this should be easy to understand by looking at this drawing here. So my P of A is equal to P of A intersection E1 plus P of A intersection E2, and so on for all the subsets I have in my sample space S. So how can I rewrite my PA intersection E1 if I want to bring in a conditional probability term here? It would be the probability of E1 times conditional probability of A given E1. So if you want to represent this entire equation using conditional probability terms, I'll get P of E1 multiplied by the conditional probability of A plus P of E2 into the conditional probability of A given E2, and so on for all the n subsets I have here. So if you put it together in a simple formula, this will be sigma 1 to n of this. Now that you've calculated the probability of A, how do you find the reverse? Calculating the conditional probability of an event EI given that A has occurred. Why would I need to bother about this in the first place? Well, we'll see an example to get a better appreciation of just why. So the aim here is to study the effectiveness of an HIV test conducted in a hospital. We want to know that if a random person is given an HIV test and reported as HIV positive by the hospital, what is the probability that he actually has AIDS and hasn't been wrongfully tested? So we have some sample data here. In this particular area, 1% of the population actually has AIDS and 99% don't. The lab results, on the other hand, show something else. Of the people who actually have HIV, 90% were reported positive, which is correct, and 10% were wrongfully reported as HIV negative. And if you look at the people who don't actually have HIV, 5% were wrongfully tested as positive, and 95% were correctly reported negative. So what we're trying to find out here is that if a person is tested positive, which would be any of these two possibilities, what is the likelihood that the person actually has AIDS and isn't wrongfully reported positive by the hospital? Since the central theme of this problem revolves around a random person being reported HIV positive by the hospital, we'll start by defining this outcome as A. There are two possibilities when A could occur. The first occurrence, E1, happens when the patient actually has HIV. And we'll call this true positive as it's an accurate finding. And the second occurrence, E2, happens when a patient doesn't actually have HIV but is wrongfully reported as positive. So we'll call this false positive. So if you take the entire population of this area as our sample space, they fall under two categories. E1, which is actually having AIDS, and E2, which is being HIV negative. And my A would look something like this, as a positive result from the hospital lab contains people from both categories, E1 and E2. And what we're trying to do here is find out the probability a person actually has AIDS given that he's tested positive by the hospital lab. In other words, we want to know the conditional probability of E1 given A. And this will be nothing but the probability of E1 in A, or events common to both E1 and A divided by all possible outcomes of A. And that will be B E1 intersection A in my numerator divided by all outcomes of A. Look at this picture here. Can you see that all outcomes of A lie in either E1 or E2? So my A is whatever is common between A and E1, and whatever is common between A and E2, which implies that my denominator here becomes BA intersection E1 plus BA intersection E2. So how do you solve this? We don't know what A intersection E1 and A intersection E2 are, but I can represent my A intersection E1 using conditional probability, which would look something like this. Do I know probability of E1 and the conditional probability of A given E1? So let's go back to our sample data and see if we can find that out. We've defined E1 as people who actually have AIDS in our population. Our sample data says 1% of the population actually have HIV. So that becomes my P of E1. And my E2 is defined as people who don't actually have AIDS and is 99% in our data. So that becomes E2. So we'll write that down. P of E1 is 1% and P of E2 is 99%. What we also need to find is the conditional probability of A given E1 and the conditional probability of A given E2. If you want to solve this A intersection E2 term here. So if you look at row 2, it gives us the various probabilities associated with A or the lab showing up a positive result. The first term here correlates to people who are tested positive given that they actually have AIDS, which is the conditional probability of A given E1. And my second term here correlates to the population of people from the group that don't actually have AIDS but are tested positive anyway. So this becomes conditional probability of A given E2. So writing down these two probabilities here, conditional probability of A given E1 is 90%. And conditional probability of A given E2 is 5%. So we now have everything we need to solve this problem. A intersection E1 is B of E1 into conditional probability of A given E1. And coming to the denominator, I have the same A intersection E1 term here, which will be this. And my A intersection E2 will be P of E2 into conditional probability of A given E2. So if you substitute the values for E1, A on E1, E2, and A on E2, we get 1% into 90% divided by the same thing plus 99% into 5%. So solving this, I get 0.009 divided by 0.009 plus 0.0495, which is 0.153 or 15.3%. When you take a first look at this answer, you might think this number is too low. I mean, 90% of the people who actually have HIV are reported positive, and only 5% of those who don't have AIDS are wrongfully tested. So how can the probability of an accurate result be just 15.3%? Even though the percentage of wrongfully tested patients is just 5%, the actual numbers are very large. Let's say we have 1,000 patients who undergo this test. Only 10 are actually HIV positive and 990 are HIV negative. Our test gives us a positive result for 90% of HIV patients, which is 9 in this case, and 5% of non-HIV patients, which is 5% of 990 or 50. So out of 59 patients that are detected positive by the test, only 9 actually have HIV. So these kind of calculations are extremely useful in understanding the effectiveness of various real-life systems, whether we're talking about the effectiveness of a social welfare program, a drug trial, or even an educational program. And the person who actually came up with this calculation was an 18th century British mathematician called Thomas Baye. And what is interesting about Baye is that he never published what would go on to become his most famous accomplishment. These notes were published after his death. So what we'll do now is to come up with an equation to represent this conditional probability of E1 given A. So if we go back to our previous diagram here, conditional probability of EI can be expressed using this standard equation, which will be PA intersection EI divided by P of A, or events favorable to A. We just calculated that P of A can be expressed in this way: intersection of A with all these various subsets in my sample space. So what we want to do is to represent this entire equation using conditional probability terms. So we'll start with my numerator term. A intersection EI is equal to the probability of EI into the conditional probability of A. So my numerator becomes this. What I also want to do is to modify the denominator such that I get similar conditional probability terms there. So if you go back to what we did in the earlier part of this video, my P of A can be written this way. Putting this together in a more concise fashion, I get P of EI into conditional probability of A divided by sigma 1 to n of this. And I'm using a different notation j in the denominator as we're already using I in the numerator. And this is what is called the Bayes theorem.